to tell you that I didn't find it shocking but surprising to find his name in IMDb, the Internet Movie Database. If you go there and look for him, you will find him. Well, he has a PhD back to astrophysics. He has a PhD in astrophysics from the University of California in Berkeley. He was a member of the Kobe satellite team that discovered the temperature fluctuations in the cosmic microwave background. There, he worked with George Smoot, and who won jointly with Mather. The Smoot and Mather were awarded the 2006 Nobel Prize in Physics for their discovery of black body form and anisotropy of the cosmic microwave background radiation. In this context, I'm sorry for taking your time. I can't resist the temptation of reading to you his thesis title and on one quote from his conclusion. The title of his thesis is Correlation Function Analysis of the Kobe Differential Microwave Radiometer Sky Maps. Differential Microwave Radiometer stands for DMR. And to quote the conclusion in his thesis, in this thesis we have presented in detail two-point correlation function analysis which helped lead to the DMR discovery of CMB anisotropies. Until the Kobe DMR detection, the absence of anisotropy in the CMB was taken to be one of the important failings of the Big Bang model. In 1980, Burbidge pointed out, if no fluctuations can be found, we have no direct evidence of all that galaxies are formed at early epochs through gravitational instability. Well, that was the quote from his, the last chapter on the conclusions in his thesis. So, unquote. He's presently the convener of the Australian National University's Planetary Science Institute. He holds a joint appointment as an associate professor in the Research School of Astronomy and Astrophysics and also Research School in Earth Sciences. Before his appointment in ANU, he held a postdoctoral position at Strasbourg Observatory and University of New South Wales, where he taught one of the most popular general study courses called Are We Alone? And that's why we are here today to hear his colloquium on astrobiology, exoplanets, and trying to answer the question, are we alone in the universe? Charlie, it's all yours.
Thank you. Thank you very much. All right. Well, thank you, Uday, for that flattering introduction. So yes, this is me right here, and this is my favorite cartoon. And it's my favorite cartoon because we have a big brain here, and many of us think that because we have a big brain, we can ask this wonderful question, what is it all about? On the other hand, there's another alternative here. It says everybody else knows what it's all about, and we have our big brain that's confusing us about what it's all about. Now, this should change here. All right, so I thought I'd give you a few words about me because you don't know who I am, and I thought I'd tell you who I am. So I was born here in the same hospital as Samuel's wife. We found out last night. There you are. And so I was born here. Then I lived about a year in Nigeria, and I lived about a year in Egypt, and I lived about 3.5 years in Germany, and about 5 years in France. Here's where I flew from 2 days ago, here to Kuala Lumpur, and then over here to Bangalore. I lived in Japan for 3.5 years, and so I've traveled around the world. I like traveling and learning languages, and I guess, and can you guess what this map is? Population. So this is the population map of countries. All right. So this is the microwave background map we made in 1992. And here is me with George Smoot. Right after our discovery, we announced this in April, and then here picture was taken by People magazine, and so we got lots of press because of that. And here is the 2006 Physics Nobel Prize. Here's George Smoot, my PhD supervisor, and this is the map we made. And John Mather is over here, and here is the map that they made. So he got the Nobel Prize for this map. And it's a little bit of a joke because what they did is really find the spectral form of the black body, right? But when that means it's a constant temperature. Remember, this is a few times 10 to the minus 5. The dynamic range of the temperature is really exaggerated to make this map. The red is the galactic contamination. I should point out, if you have any questions, just interrupt. I like to interrupt speakers as much as possible. I get in trouble that way, but feel free to just interrupt and call out and say, what about that's wrong because good. All right. So here's the paper in 1992, and I look back at this paper, and you talk about the correlation function. These are the correlation function plots here, and these are the only two plots in our discovery paper. And I made both of them because I was George Smoot's only PhD student at the time. So, and the signal that we're talking about is right here, as opposed to no signal here. And here's a function of the galactic cuts. But let's move on. One of the things that I've been known for is this particular paper, and it's the age distribution of terrestrial planets in the universe. So, this was 2001, and you can see the time. Here's the Big Bang. Here's now. Notice I have 13.4 billion years after the Big Bang. Now it's 13.8. And so up in the top here is the star formation rate. This is the star formation rate, starts low, goes up, and then it has been coming down. And this is a logarithmic plot right here, right? So here's where the sun formed, and here we are today. Now, these stars, of course, burn hydrogen into helium, helium into carbon, oxygen, silicon, iron, etc. So they're the ones that are currently polluting the universe with all of these non-hydrogen helium. And that pollution we call metallicity. Fe on H is a measure of that. And so it just grows and grows and grows. It's kind of like garbage if no one takes it away. So the universe is being filled up with this garbage called metallicity. And that's important because you, the Earth, and all life on Earth is made out of these pollutants. You cannot make life out of hydrogen and helium, we don't think. So if that's the case, then this is a measure of the potential for making Earths and making life. And so when you then put this together and say, hey, you know what, I need about this much metallicity in order to make rocky planets, then this distribution turns into this distribution. And this becomes the age distribution of Earths in the universe, rocks in the universe. And essentially the same distribution as the star formation, except for the first 1.5 billion years or so, is cut off because those stars did not have silica, did not have oxygen, did not have magnesium. So this becomes the best estimate at the time of the age distribution of Earths in the universe. And notice that our sun and our Earth is young compared to this distribution. 2/3 of the Earths in the universe are older than ours. As a matter of fact, the distance between us and the mean is about 2 billion years. So if you think that once you get a rocky planet in the universe, a wet rocky planet, that you get life, then the life on most 2/3 of the planets in the universe has had 2 billion years longer to evolve than the life on this planet. That scares some people, because if you look back at the evolution of life on our planet about 2 billion years ago, our ancestors, we were all amoebas. So that was the kind of life that was around about 2 billion years ago. There were eukaryotic life for that, and that was after the great oxidation event. Is this plot clear?
Apart from
Speak up loudly, please.
yeah, apart from the toxins, you also need some supernovae, right? To send the toxins out into the stars.
Spread it around, yes. Matter of fact, that's the subject of the next plot here. Okay, so in 2004, we published this plot on the galactic habitable zone. So the idea is, here's the galactocentric distance, so 5 kiloparsecs, here's the sun at about 8 kiloparsecs, and here's time before present. Here's today, here's 6 billion years ago, here's where the sun formed, and here's where the thin disk of the galaxy formed, somewhere around here. Notice that too many supernovae can be dangerous. If you have a supernova next door, that can wipe out, that can do dangerous things to an atmosphere of a planet. And so, but these are the things that also produce the metals. So it's kind of like a fire. You get too close, it hurts you. You get too far away, you don't have the metals that you need to make an Earth. And that's the nature of what is called the galactic habitable zone. Any questions on that? All right, I'll move along then. So I'm here to talk about astrobiology. And astrobiology is a new science, and if you want to roughly date when it started in, you could say, 1995 or so. Astrobiology is a name we use now, but it used to be sometimes called bioastronomy, sometimes exobiology. And people used to tease it, says, hey, it's a science without a subject matter because we haven't detected aliens yet. So, on the other hand, we have the Nobel Prize in Physics, 2019. was awarded to Didier Queloz and Michel Mayor. These are two Swiss scientists who used a very new, accurate spectrograph called LOD to find something very unexpected. That is a 4-day period of a planet that was something like half the mass of Jupiter. And so it was orbiting in 4 days. And that was not something we expected based on, oh, if there are planetary systems out there, we should expect them to be like our planetary system. Remember, Mercury's orbit is at 88 days. This one is 4 days, so much, much closer in and much, much heavier than Mercury or the Earth or Uranus and Neptune. All right, so I'm having trouble here. This thing's not... So here's the paper that they got the Nobel Prize for in Nature. And here's the plot of the discovery of this planet. Notice it just got a pretty good signal to noise, the sine wave, and the period is about 4 days. Now also, the year later, that was in 1995. This is 1996. A press release in NASA on the 7th of August, life on Mars. Are there fossil bacteria in this Martian meteorite? And based on, and then there was a big brouhaha, lots of news, and then NASA decided to start the NASA Astrobiology Institute. So astrobiology became pretty heavily funded, or started to have lots of funding in the US. Now, I wanted to show you the progress that has been made over the past 20 years in exobiology, finding exoplanets, because that's one of the most scientific versions. As soon as you get into biology, it becomes, you start to wave your hands and say, what is life? But here we're talking about planets. You're physical scientists, most of you, and therefore you can identify with, detect plots like this. So here's the period, orbital period of a planet. Here's the mass of the planet, and here's our solar system. Mercury, Venus, Earth. Earth, you can see, is 365 days, and it's about 1/300th the mass of Jupiter. There's the mass of Jupiter right there, and Saturn, Uranus, Neptune. So that's where our planetary system is. Now, the first thing to notice, so we're going to start in 1995 and keep a look at these dates. These dates will change from 1995 to 2015, 20 years, and you will see planets starting to be detected here. Now, this is very important that you do not think that this is what the true distribution of planets is, because here's where we can detect things. Why? Because they have short periods and they're very massive. That produces the largest amount of signal. So in other words, the largest signals are here, the weakest signals are here, and so we're struggling to detect these things. So of course we're going to see things here first, and then as we get more and more sensitive and look for longer and longer, we will start to see things over in this part of the diagram. So let's have a look at this movie, and keep your eye, as I said, on that number here. That starts in 1995, and you can see there are already about 4. I should say that in the beginning, this is radial velocity, and that's what I showed you, the Mayor-Queloz plot. That's a radial velocity plot. That's in the first 15 years or so, almost all detections of exoplanets was with that technique. But with the advent of, well, looking carefully for eclipses, that is, the dimming of starlight due to a planet passing in front, and then finally with Kepler, you will see an amazing number of points pop up at the end of this movie. So let's have a look at how this goes. 96, 97, 98, 99, 2000, 2001, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, Kepler, 12, 13, 14, 15. Now, this has gone on for the past 25 years, and there are many more than we have shown here now. And so we have 4,000 or so. It used to be the case in the first 5 years, whoa, you get a big press release if you detected any planet. Now you can detect 100 planets and it doesn't make much of a splash because, well, we have 4,000, we have 5,000, so what's another 100? But what's important here to notice is, look where these things are being detected and look where our planetary system is. Basically, if our sun was in one of these targets, they probably would not have detected any planets yet, because you can see that we're right on the edge of the sensitivity of these instruments. Now, TESS is a new satellite launched by MIT about last year, and one of the beautiful things about it is it's full sky. Kepler looked at a tiny fraction of the sky near the constellation Cygnus and looked at 200,000 stars and then just did that for 3 years. It's the most boring experiment ever done. You just look, stare, just pure staring, but with very good photometric precision. And that's what enables them to get these stars, these planets. And because they looked so long, they could get longer period ones. TESS is doing full sky, so all the whole sky, but they're only looking 27, about a month here, a month here, a month here. So all of their planet detections will be limited to less than a month. Here's 100 days, so they'll be limited to this side of the plot. And notice that the Earth is on that side of that line that I just showed. So TESS is not going to find Earth-like planets, except if you have an M star. The habitable zone around an M star has 10 or 15 day periods, in which case TESS can find habitable rocky planets around M stars, not G stars like ours, but M stars, which are 1/2 to 1/10 the mass of the Sun. And there you have a problem. If you find a rocky planet in the habitable zone around an M star, maybe there's something wrong with that, because the pre-sequence Hayashi track that goes down into the main sequence is almost straight down in a Hertzsprung-Russell diagram, which means that the luminosity used to be 10 or even 100 times more than it is today. And to talk about a habitable zone, you say, oh, that's the brightness of the star today, but that same planet that's in the habitable zone used to have a star that made it way, way closer. Well, what I mean is, the star used to be so much brighter that maybe it got completely devolatilized. Good question.
So when you say
Loudly, please.
Yeah,
Loudly.
so when you say habitable zone, you mean like similar temperature?
Habitable zone is essentially when you assume an albedo of, let's say, 0.3, like the Earth, and then you know how bright the star is, and you know how far away it is, then you can say the effective temperature is something close to the temperature consistent with liquid water at the surface. It assumes you have to have some pressure to do that, right? Because if you had no atmosphere, you have to be big enough to have an atmosphere to have liquid water. Yes? Are these rocky planets? Well, recently when we do very careful analyses of what is rocky and what's not, I should point out that this is just period and mass. But when you have an RV detection, it gives you the mass, and if you have a transit detection, it gives you the size, and because you know it's plane on that you're looking at it because of eclipses, you know that the sign I ambiguity here goes away, so you get the mass from radial velocity, you get this size, and that gives you the density. If you know the density, then you can say, you know what? I know the density of these guys. Saturn floats on water, you may know. So the density of Saturn is less than water. And this just barely floats, just barely sinks. And these are gas giants or ice giants, and they have a lower density. These guys are rocky. They have densities on the order of 4 or 5 grams per centimeters, and these have 1 or 2. So there seems to be in our solar system a dichotomy between large ones and small ones. Where that change happens looks like it's about 1.5 or 1.6 Earth radii, somewhere around 8 Earth masses. And the reason we think that is because when you have a body inside of a protoplanetary disk that still has hydrogen around, if you form a core that's more than about 8, then you have exponential infall of the hydrogen and helium, and that's why these things are gas giants. Here, because that's the hand-waving version. Any other questions? Yes? Loudly, please.
Radial velocity measurements, what is measured is in spectrum.
What is measured? Okay, have you been to a car race? If you go to a car race, you'll hear this, right? Doppler effect, right? So here's a star, and here's a planet, and you're an observer, right? Now you cannot see the planet. It doesn't shine. It reflects, but the reflection is too little. You can see the star. Now, you know that this they don't orbit here, they orbit the barycenter. This thing orbits the barycenter, therefore it's going like this. When it's going like this, it has a radial velocity towards you. Here, nothing, and here's radial velocity away from you, so you get blue shift, red shift, blue shift, red shift. So then you look very carefully at the lines in the spectrum, you see the lines go, and then that tells you what the period is. And it also tells you what the M sin I is, because you don't know whether it's like this, or if it's like this, you can't see anything, because the star is going like that. No radial velocity. So it's only, if you have a system like that, you can't see nothing. You won't detect. And transit's interesting, because transits have to be exactly like that in order for it to transit, to eclipse.
And how do you know whether it's a rocky planet?
Loudly, please.
How do you know whether it's a rocky planet or not? What is that?
Well, one thing is we suspect that the smaller ones are rocky and the bigger ones, the more massive ones, are gaseous. But now, in the past 10 years or so, we have stars for which we have radial velocity and transits. When we have that, we have M and we have R. That gives you density. And the density, is it 5 or is it 2? And if it's 2 or 1, then it's the gaseous one. And if it's 5, then it's the rocky one. And you can see a change if you plot M versus R. You see a fitting line here, and that fit changes when you get to R above about 1.6 Earth radii, about 5 to 8 Earth masses. So this is something very new. This is what I have a student doing now, trying to figure out what's the best fit to that and how accurately can we predict where that changes. And maybe it's kind of smooth because maybe you don't go from rock to gas, maybe you go from rock to a water planet. And maybe you go from a rock with a big, small atmosphere to a rock with a bigger atmosphere. And there are all kinds of problems with this because some gases are more opaque than others, and you're trying to get the size of the thing, and the size depends strongly on how opaque the gas in its atmosphere is to the light that you're using to measure its size. So you have a frequency-dependent size that you then have to play with to help you understand what the atmosphere is made of. You got a question?
Yeah. So
Loudly, please.
yeah, you were talking about the M star and the planet around it and whether the life can be sustained on it or not. But the formation of the planet may not be at the time of the pre-main sequence evolution of the star itself.
All right, so the question is, how simultaneous is the formation of the star and the formation of the planetary system? Well, stars form by accretion of a gaseous and a dust disk, right? And the time scale for the formation of stars is on the order of 10 to the 5 or 10 to the 6 years, okay? Now, when we look at stellar nurseries, we see hundreds or thousands of stars forming at the same time. And when we look at very young ones that are 1, 2, 3, 5, 10 million years old, we can see the fraction of those disks that are still around. And so we can estimate the time scale at which those gas disks go away, leaving presumably planets. Now, and that's when, if you have a Jupiter-like planet, you know it has to form before the gas disappears. So that's how we know that Jupiter formed, for example, within the first 3, maybe 5 million years. So that forms early. Rocky planets, at least the models I've seen, they form even earlier. The center of those gaseous disks hollow out very, very early, even before the rest of it goes away. So there, the rock is left very soon. The problem with the formation of Earth and why it takes about 50 million years or so, at least in the context of the Earth, our planetary system, is what's called oligarchic growth. You have objects the size of Mars and the Moon banging around. It takes a long time for them to collide into each other so that you have an oligarchic growth, and so you only have 4 planets in the inner solar system rather than 300. But that oligarchic growth is what takes the time. But your question is about, okay, I just talked about the star, our sun. Now let's go to 1/10 the mass. How do all those timescales scale with the change in the mass of the star? And I don't really know. But I've assumed that they're kind of the same. I should say that the pre-Hayashi track of the sun was about 50 million years, and that's the order of the time scale it takes this Earth to form, finally, to accrete something like 98% of its mass. And I'm not sure how that would scale when, during the 500 million to 1 billion year long pre-main sequence Hayashi track of an M star, where that would form the equivalent of these rocky planets, which we are now seeing in the habitable zone. So the answer to your question is we don't know, but we make some assumptions about it, and the assumptions are what I use to make that statement.
Yes. Another point is that we do not know where or when water came onto the Earth.
Well, we have lots of ideas about water on Earth, but mostly based on the D to H ratio. So we have a D to H ratio on the Earth. On the other hand, D to H ratio on the Earth has been changing, basically because you have H2O and D2O, and the D2O hangs around and the H2O is lighter, so it escapes. You have Rayleigh escape, all kinds of escape. And every planet in the universe is now losing hydrogen, preferentially over deuterium. And so that raises the D to H ratios everywhere. And so we say, well, what was the original one? Well, that's probably what the sun is, or probably what Jupiter is. The sun can't be used because it burns the deuterium. And so we We can't get the primordial D-H ratio of the sun from looking at the sun because the sun has burned its deuterium. So what we do is use Saturn and Jupiter as a proxy for the proto-D-H ratio, and that's what we use to try to estimate where did the Earth's water come from. Basically, the outer asteroid belt had about 3 AU, 3 to 3.5 AU. It has something like 5, 10, maybe even 15% water content to these objects. So when they get radially scattered, then boom, when they hit the Earth, you get lots of water. And so the ideas that we have today are that we had radial scattering that brings water in from beyond the snow line, and that's how we got the water.
True.
That's probably that's the standard conventional model. How sure of that, we need a lot more evidence to back that up.
That's true. If that is the case, then the 50 million years is not necessarily a time for support for life on planet around M star. That's my point.
50 million years is irrelevant for the M star because you have a 2 billion year period, or not 2 billion, half a billion to a billion year in which your star is significantly brighter than the star luminosity that you used to create the habitable zone. So in other words, the planets in the habitable zone around an M star today that TESS is finding probably have been devolatilized many times over if the radial mixing that we just described happened early enough so that its star was bright enough so they could then devolatilize that. It really depends on the dimming of the star compared to the radial mixing of these objects beyond the snow line, which sometimes come in and hit.
You mean the dimming happens over half a billion years?
Yeah. It's a very long, almost vertical Hayashi track. There's a question back here. Loudly, please.
So, stars with multiple planets, so they might have a very complicated radial velocity clocks, right?
Yes. Yes, they do.
But is it possible to get the information for
Yes.
this kind of
Here's how it does. You see that plot, the radial velocity plot of the 51 peg, right? So what you do is say, okay, you do a best fit to that, and then you subtract it out. And then you look, do I have anything left? If you have anything left, you fit another sign to it, you subtract it out. You look, do I have anything left? Ooh, maybe that's another one. And so that's how we do it. There's nothing too confusing about it, just a sign fit, remove it. Sign fit, remove it.
You explain the word you use, devocalize?
Say it.
You use the word like something like
Devolatilized. Devolatilized. Now, the Earth is a devolatilized piece of the sun. So if you take a piece of the sun, get rid of the remember the sun is about 1.4% by mass non-hydrogen helium. So you take a big ball of the sun, about 100 Earth masses, get rid of most of the hydrogen, maybe leaving 1 part in a billion, get rid of almost all the noble gases, leaving 1 part in a billion, get rid of everything that's volatile, like water, like CO2, like nitrogen, get rid of all that, and then you have the Earth. And what's left, another way to think of it is, the most abundant elements in the universe are hydrogen and helium, so get rid of that. But some H is in water. Water is sometimes frozen, so it stays around a little bit. But the next two abundant ones are oxygen and carbon. What do? They form carbon monoxide. Now, if there's this much oxygen and this much carbon, then the carbon and the oxygen here form carbon monoxide and get out of the system, leaving this much oxygen. This much oxygen then combines with silicon, iron, magnesium, calcium to form the rocks that you see out there. Right there, the cement here. So this is just silicon and oxygen right there. A little bit of magnesium, a little bit of calcium. That's because we got rid of most of the carbon. Only a tiny bit of carbon is left on Earth compared to the carbon that was in the sun. And so that really, although we're life forms based on carbon, we have been decarbonized when we were devolatilized, when the CO just went out of the system because it was a volatile. So that's what I mean when I say the Earth is a devolatilized piece of the sun. Okay, moving right along. So that was the movie. But I guess the main point I wanted to make here is that, again, here's where we can see, and here's where we can't see. And so, here's, wait a minute. All right, so here's 2012, and here's 2017. And this slide just gets denser and denser and denser. And, but remember, TESS will only be able to fill out things here, not out here. All right. So, So I guess I wanted to make the point, this is a general point in science that I've come across again and again and again as I do modeling, and that is, if you can estimate the sensitivity of your instrument, let's say of any parameter x, here's the sensitivity of your instrument. That means you can detect, oh, x is up to here, and then it goes down, down, and then it's 0 beyond there. Typically, you have some sensitivity function like that. If you can measure this very, very accurately, that gives you an incredible handle on changing what you see to the underlying distribution. And so here's a little diagram of that. Here is, let's say, that's the true distribution as a function of x of any parameter. And there's your sensitivity, right here. So then what do you get? This is what you observe, right? You observe this. And what you do, if you're a bad scientist, you say, what you see is what you get. If you're a good scientist, you say, that's crazy, I know what the sensitivity is, I can deconvolve the sensitivity and then get this distribution pretty well up until about here, and then the error bars blow up because the uncertainty on your sensitivity is finite, and then it goes to 0, and so the error bars here blow up the true distribution that you're deconvolving. In a math equation, it looks like that. So here's what you observe, and then what that is, the true distribution involved with the sensitivity, then you just do an integral, and then you get the observed. But then, if you know this very well, then, and you observe this, then you can get this back out. I think any good scientist knows this, but I just wanted to make the very important observation that knowing what this is really important.
Is there an integration there?
What's that?
Is there an integration there?
Yes. Should there not be?
Yeah, what is x on the left hand side?
X is the x variable here.
On the left hand side.
On the left-hand side, that's this here, it's
But you
green.
integrate on the x, not on the right hand.
Yes, I did that wrong, didn't I? Maybe you can talk about the correct formula here. I wrote this very quickly. What should, I'll talk to you later about what that should be.
Without the integral?
Say it?
No, it's a convolution integral and the convolution variable is missing.
Just t of x minus
We have 4 people are going to tell me what it is after class. All right, but I think you know the idea. That's the basic thing. And the idea is get the sensitivity so you can back out the true distribution. All right, so the result of this is that every star probably has some kind of planetary systems. Sometimes you'll read there are more planets in the galaxy than there are stars, but that's a little bit, I would say that, well, every star probably has some kind of planetary system around it. That's something we did not know, and that's what you get when you do this deconvolution of the sensitivity, where you're sensitive to the things in the upper left, but not sensitive to the ones in the upper right. If you know the sensitivity, then you can extrapolate a little bit, and then you get this result. Okay, so here's some stars. Now, some of these stars, like the Earth, have produced some kind of life on them, and others, they don't. There's no life. So the question in astrobiology is to try to figure out, are we alone? Is there life on these planets? I just showed you that there are planets everywhere, and I guarantee you that there are lots of wet, rocky planets, billions of them in the galaxy. But then you say, oh, they Earth-like or not? Well, of course, Earth-like really is a subjective statement. How Earth-like do you need? Just wet and rocky? That's one way. Wet and rocky with 30% of the surface covered with rock and 70% ocean? Or can it be between 0.9 Earth masses and 1.1 Earth masses? Or how low can you go and still call it Earth-like? So it's a very subjective thing, and we're trying to work that out. The reason why it's subjective, but we need to get that a little bit more objective, is because what we're interested in on Earth is whether those other planets have life. That means we need to ask the question about Earth-like, what are the most important features of a planet which promote the origin and evolution of life? That's where we don't know much. And so where it's hard put to say, that's an Earth-like planet in a way that would make life. And that's the burden, the challenge of astrobiology. All right, so a few decades ago, here are let's go here. Here's some extraterrestrial environments known to exist. These are exoplanets. In the last few decades, this thing has just blown up from just our solar system, maybe other planets, to thousands and thousands and billions of planets. And then the biologists on Earth haven't been lazy. They've looked in all these weird environments. They've looked in hot places, cold places, dry places, wet places, highly acidic, highly basic, high and low salinity. They've looked all over the surface of the Earth to see where is there life and where isn't there life. What are the boundaries of life? And they found, to their surprise, that life is almost everywhere. And that's why this thing turns into this. And what we're interested in is seeing if there's any overlap between the environments which are compatible with life and the environments on all of these planets. That's what we're looking for. These guys here, habitable planets, and then inhabited planets. Because there's a subtle distinction between one that's habitable, where there's no life, and habitable where there is life. All right, so we have to look at the history of the Earth and the history of life on Earth and how it got there. And so 4.5 billion years ago, the sun was some overdensity in a molecular cloud with molecular hydrogen and helium. And then 4.5 billion years later, we get this. So this is something that happened on Earth. This is a 2-slide movie of the evolution of life on Earth. And I have these are the names of the elements which make up about 98, 99% of the composition of you and the trees and the bacteria everywhere on Earth. Fungi as well. So life, we know, is made out of these. Now that's kind of an interesting thing because these are some of the most abundant elements in the universe. There's nothing special about the elemental composition of life. We know that. It's not made out of some rare iridium or unobtainium. It's made out of this stuff. And so here, because I'm a cosmologist and an astrobiologist, I have the privilege of writing on one slide the entire history of the universe, including stars and life. So here we go. We start with the Big Bang, and we have hydrogen and helium overdensities. They have stars. Big stars go boom. Little stars just sit there for billions and billions of years. The big stars go boom, and they produce iron and oxygen and nitrogen, and then that's the contamination in the molecular clouds, which then forms next generations of stars, which have these little pieces of rock contamination around them, which we call rocky planets, where this is one right here. And then if you're a scientist, you study these sciences, and we have made phylogenetic trees based on rRNA, ribosomal RNA, of life on Earth, and we can create how things are related to each other. So here are, let's say, here are eukaryotes, here are animals. That's us, we're animals. We're more closely related to fungi than we are to animals. I did this plot about 15 years ago when we thought that fungi and plants were more closely related than they are to animals, but now we know that fungi and animals should be together, and then come plants. Notice there are chloroplasts that go from here to here, the mitochondria that switch over from bacteria over to eukaryotes. And now we also know, well, anyway, this tree has advanced, and lots of progress has been made on understanding the relationships between the life forms on Earth. This is really important for exobiology, or for astrobiology, because we want to know how life got started here. If we want to get to that scientifically, we have to go deeper and deeper and deeper into this tree to see what the earliest life forms were like, what was their metabolism, how did they live, what were they made of, how were they different from today's life. So I spend most of my time as an astrobiologist getting rid of the literature on eukaryotes. Because eukaryotes are something that, look, eukaryotes are right here. They are a side branch of the archaea. So you have to get rid of all the eukaryotic literature and then study the differences between bacteria and archaea, and then the deeper roots of those two. LUCA, it's called the last universal common ancestor. And that's what we do as astrobiologists. Any questions about this plot? Yeah?
Previous
Loudly, please. Previous slide.
Yeah.
This.
I think
Before that. Before that.
Right. So you mentioned that life is found to exist in almost all environments.
I wouldn't say that. Life is really, we talk about a biosphere, but really it's a bioshell. The Earth is has a radius of 6,400 kilometers, and life is on just a thin film about 6 to 10 kilometers. So it's about 1/1000th of the radius. So if you take a meter stick, put one end in the center of the Earth, the other at the surface, and then that surface of life, that bioscum, that bioshell, is only about 1 millimeter. So that's how thin it is. But what was the question?
The question is, on the second part of the figure, you have an overlap region and and you have region below where you don't find life.
Yes.
And above, of course, you have life.
Well, we have life on Earth. We don't know if we have life elsewhere.
Absolutely. So the environment, they're represented by the
Here?
not intersected one below that,
Yeah, here.
is not to be found on Earth.
No, these are extraterrestrial environments known to exist, like other Jupiters, like the 51 Peg, and all the other exoplanets, which are not in the habitable zone, or they're too small, they don't have atmospheres. We're finding all kinds of planets which are incompatible with what we think life is.
So what is the environment which supports life in general?
For as far as we know, when we say the word life, we have to talk about terrestrial life, right? Unless you want to speculate about other kinds of life, but that's another ballgame. But the most conservative astrobiologists say, you know what, we're going to go looking for life, but because we don't really know what life is except for what we have here, we're going to look for environments compatible with the life we do know. Now that's a limited, conservative way to go, but it's one way to go. Other more speculative say, wait a minute, maybe you could have silicon life, maybe you don't need, maybe you can make it on hydrogen and helium. Maybe you can have life on the surface of a neutron star based not on chemistry, but on nuclear chemistry. There's some people who have written about that. We really have a very poor idea of the far limits of life, and I'll talk about that later in the talk.
If you have a clear idea of that, you can go for looking those concerns.
If you did, but we don't. And I want to convince you that we really don't. Because most people think, oh, we have a good idea of what's life and what's not life, and I want to destroy that impression as much as I can. Yes?
So are we taking into account of viruses also?
Well, I've done a survey of this. I'm very interested in viruses, so I've gone around the world. I'm making a MOOC, a massive open online course called Are We Alone? Well, How Did We Get Here? And as part of that, I interview biologists all over the world. And when you ask biologists this question, a quarter will say yes. A little more than a quarter will say no. Another quarter will say, I don't know. But the smart ones say, that's an irrelevant question. It doesn't make any sense. And I'm in that category, and I'll show you why later on. Are you a biologist?
Yes, sir.
Are viruses alive?
So viruses need a host. That's
Do you need a host? You're breathing
viruses
oxygen
need a
right now.
host to be alive.
Do you need a host? You're breathing oxygen. Yes, of course you need a host. You're breathing oxygen that was made by these plants. So you're living in an atmosphere created. It's kind of like a big cell around you. You need a host. And that would be my argument, not being
No,
wrong.
but it's like viruses have a protein and an RNA. They don't have a cell as such. So even if with that, like we have this theory that RNA later evolved to be the DNA, and then
Yes.
things came around.
Yeah, we have
and
good
cells
evidence that
came
RNA
around.
preceded DNA. That's very good evidence that astrobiologists are well aware of. And that's one of the reasons why I think that we should go looking for viral life. But I disagree with you. You think viruses are not alive. I think they're sure. Matter of fact, most of the organisms on Earth are viruses and nice. Anyway, you can see the debate here. This is what happens when biologists start talking about life. Okay, moving on. This thing. Okay, so here, you are here, and you are here. But if you're a biologist, you also have this new thing, and you are here. And this is a new tree of life, and here are all the bacteria. Here's something called CPR, which is a new group of bacteria. You can see how this is based on metagenomics. All the things with red dots have not been cultured, but they're put in this tree because they have been sequenced. In those sequences, we have really smart computers now that can tell us, you know, I go in, take some soil, get rid of all the dirt, get rid of all the rock, and then find the DNA, break up the DNA in pieces, then put the things together, align them, and then you come out with these species here. It's called metagenomics, and this is Jill Banfield's group, and we are right here. Now, you may have heard of 3 domains of life. Well, this shows that there are only 2 domains of life, and that the eukaryotes, that's here, this is the fungi, and here we are, right here somewhere. This group, look at how it attaches, right there. So it's deeply rooted in the archaea. These are all archaea. So eukaryotes are a type of archaea. We have a couple of things that have come over, like the mitochondria inside your bodies, that have come over from bacteria. Also chloroplasts. They used to be alpha proteobacteria. For example, the mitochondria in your body that enabling you to breathe oxygen now and turning into ATP. So you are here. This is an astronomer's, you are here. This is a biologist, you are here. And what we're really interested in is getting what's here at the origin of life. Because in general, the closer you can get to the origin of life, the closer you can get to what I call deterministic chemistry and physics. Because the chemistry and physics we know is the same everywhere in the universe. everywhere in the universe because we can see what the stars are made of. And we can see those rocky planets forming elsewhere. The chemistry and physics are the same. If you're a chemist and a physicist, you are qualified to practice on Alpha Centauri. But if you're a biologist, that's another thing. So here's the observable universe, and here's if you look at a tiny fraction of it in the optical, this is what you see. And this is from the Gaia satellite. This is our galaxy, the Large and Small Magellanic Cloud, which you can see from my backyard in Canberra, because it's such a little city, and these things are, but they're kind of faint, but you can't see them in Sydney. And here's your observable universe here. So I wanted to talk a little bit about scale. So physical sizes, forget biology for a second. So you have 1 centimeter, you have pebbles, and then we're going to talk about small things over here, big things here. So we have an electron in an iron cage of 10 to the minus 16 centimeters, and then we have here space-time foam at about 10 to the minus 33 centimeters, and then we have at the size of the solar system 10 to the 16 centimeters, and then we have 10 to the 33 is the observable universe, and then maybe we live in a multiverse in which you have, I don't know, 10 to the infinity centimeters. I'm not sure how big spatially. Maybe our universe, the observable universe, is certainly not infinite, but our universe may be infinite, and maybe that infinite universe is part of an even larger multiverse. That's why we have 10 to the infinity there. Anyway, we have a lot of big things, and we have small things. And there's no biology involved here, but I thought now I want to add biology to give you an idea of the size of the things that we call life forms. So, there's 66 orders of magnitude between the observable universe and down here, space-time foam. And here are the biological sizes. Here's like a 1 centimeter multicellular organism. Here's a unicellular organism. These are E. coli. And there are viruses on this is called a pilus. And these are viruses, these are bacteriophages trying to get their DNA inside the pilus and then make its way into the bacteria. And you can see that there are more of them than there are of the E. coli. And then you have viroids. I don't know if many of you have heard of viroids. This is a new type of thing that was discovered. Here's a viral DNA, and here's the viroid. This is a potato spindle tuber virus. This is a new type of life form. It's not a virus, because viruses have capsids. Some viruses have envelopes around them. These are viroids. They do not have capsids. They're just a piece of floating DNA that floats around and then goes inside an organism and comes out. It does not have a capsid. That's why it's called a viroid rather than a virus. And then we have things called, and those are viruses right there. Then we have things with genes that are even smaller. And then we have prions. And you can argue about whether prions are alive and whether genes are alive or whether viroids are alive or viruses are alive. Anyway, you can argue about anywhere around here. And then we have ecosystems. Some people think they're alive. Other people say, well, that's crazy. Well, it's not an individual, so it's not alive. Well, maybe it is. I don't know. And then we have things called Gaia. And you'll have biologists arguing about whether the whole bioshell, the whole biosphere, is a life form or not, or can be treated as a life form. And this is all involved in what's called the debate about the unit of selection in biology. Whether the unit of selection is the gene, as Richard Dawkins would say, or as most biologists would say, it's the individual. But the individual is something that also has evolved, has a history. And we have 10 to the 9 centimeters and 10 to the minus 6. So life, as usually understood, disappears as we go to either end of this size range. So that's kind of like a size understanding of what life is, or a misunderstanding, we don't know. 15 orders of magnitude. Humans at the 10 to the 2 centimeters are in the middle, somewhere here. And it seems that we have conceived the word life, so we are the epitome of it. And how objective can that be? And I think we should keep that in mind as we study other life forms, because we want to say, well, what is life? Well, the basic assumption is that we're alive. And now we're going to say, okay, how small can it get? How big can it get? But that's kind of a human-centric way of going about these things. As physicists, you know, we don't like to talk about being too human-centric, right? We like to look at things that we can see with X-rays and gamma rays and radio, not just the ones that we can see with our eyeballs. Okay, so here are the physical sizes. And with biology, there's those 15 orders of magnitude between here and here. I guess if you had I talked to some of my crazy friends, they would say that maybe galaxies are alive or stars are alive, but it depends what you mean by life. And let me talk about that a little bit. Anyway, there are lots of Earth-like planets, probably 10 to the 22 in the observable universe. The universe looks like it's spatially infinite. And so some people would argue, you know, take it Uday, what's the probability of you, and I don't know, 10 to the minus 2 billion or something, right? So it's a really small epsilon, but if you multiply epsilon times infinity, you get infinity. So there are an infinite number of u's in the universe if I can assign a probability epsilon to you if the universe is spatially infinite. So, and people hear that and say, what, that's kind of crazy. An infinite number of Udays? Is that the kind of universe we want? but there's a way out of that, and it has to do with sets of measure 0, but I won't go there today. So we have this question, are we alone? And I did a survey of this question. I've asked people all over the world, and I gave a course called Are We Alone, as Uday mentioned. And before the course, these were the results. 10% said, yes, we're alone. 80% said, no, we're not alone, there are aliens. And about 10% said, huh, what does that mean? And at the end of the course, this is like educational pedagogy analysis, very carefully done. At the end of the course, this is what you get. 20% said yes, we're alone, 60% said no, and then, increased from 10 to 20%. This is, as a structure, I'm very proud of this number. Doubling the number of people who didn't understand the question. Because I will argue that the question it's kind of an ambiguous question. What does the question, are we alone, mean? So, when you say, are we alone, when I ask that question, are we alone, what do you understand by the word we? About half of the respondents said, we humans. Now the problem with that is that Homo sapiens, although we're the only extant hominid on Earth, you say therefore we're alone, but we Homo sapiens are not the only extant ape on Earth, therefore we're not alone. And we're not the only primate or mammal or vertebrate or dinosaur. In other words, if we are not alone on Earth, and I guarantee you we're not alone on Earth, we Homo sapiens, then we know the answer to the question. We're not alone in the universe because we're not even alone on Earth. So we have an answer. But the other half of the people say, no, forget humans. Let's use life, okay? So, we, not we humans, but we the life forms on Earth, are we alone? So let's make that the question, so we don't have to deal with the ambiguities I just described. And alone. Now what does alone mean? Also I found out that alone means different things to different people. So, if we find microbes on Mars, most of the people in the world will still think we're alone, except for the biologists. Biologists say, oh, we're not alone, we found life elsewhere. But most of the other people say, no, we're not interested in your microbes, we're interested in something we can talk to. We're only interested in intelligent life that we can communicate with. Therefore, we're still alone, even after we've discovered life on Mars. So where is everybody? This is Fermi's paradox. Where is everybody? If we have all these planets, and all of them are, a lot of them are Earth-like, and if you assume that life evolves on them, and that evolves into intelligent life, and technological life, then, as I showed you in the age distribution, these other planets have had, on average, 2 billion years longer to evolve into whatever they do. If that's the case, they should have colonized the galaxy a long time ago, because the galaxy is only about 100,000 light years across. Traveling at, I don't know, 10% the speed of light, it only takes you 1,000,000 years to colonize the galaxy. The galaxy's been around for 10 billion years, compared to 10 million to colonize it at 10% the speed of light. So, where is everybody? This was in Fermi's head in 1950. So there's a silence out there. It's kind of like the dog that didn't bark in the Adventure of Sherlock Holmes' Silver Blaze exhibit. And it's kind of like the man with the newspaper in this Magritte painting. Anyway, how are we going to find out if we're alone or not? One way to do it is transit spectroscopy. So basically you have a star, you look at the star, you can't resolve it, but this is what's going on. You have a planet passing in front. The planet has an atmosphere. Here's the atmosphere, it's height here. And so the light that's coming from the star comes to you, and some of it has transited through the atmosphere of the planet. And when you do that, you get absorption lines. So here's another picture. Here's the star, here's the Earth, here's observations. Here's the planet. The star goes zoop, 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 and it goes through, as this light goes through the atmosphere, it gets absorbed by the molecules in the atmosphere. But then comes the question, what are biosignature gases? What types of atmospheres is created by life, and what type are created by just non-life? So is there a way to distinguish, through looking at the atmospheric contents, life-containing planets from lifeless planets? And that's the name of the ball game, and it will be for the next 10 to 20 years. But we have to get, if you get a big planet, it has a big atmosphere, but we're talking about little tiny pieces of dots like Earth-like planets with very thin atmospheres, and so the amount of signal that gets absorbed when you're staring straight at a star is very small, so you have to do differential spectroscopy to get at these lines. It's very crude, very rough. You can get a result, but the problem with the result is we don't know how to interpret the result yet. We don't know what gases are produced in the atmosphere. Lovelock has talked about this about 50 years ago, and he said there are some atmospheres that are in chemical equilibrium and some atmospheres that are not. And the ones that are in chemical disequilibrium are the ones that probably have life. One problem with that is volcanoes. Very few people think that volcanoes are alive. Volcanoes are sources of chemical disequilibrium in the atmosphere, but also photons coming from the sun create chemical disequilibrium in the upper atmosphere. And so, what is it? What is a biosignature? And I think I've run out of time here, so I'll stop there. And we have a couple more questions, or
Yeah.
okay.
Definitely.
All right. So, any questions?
Okay.
Question there?
Yes. Yeah. There.
Biosignature can be created even by gaseous planets. So why it should be Earth-like atmosphere, and why not the Jupiter, which is
Well, right. Well, what you really want to do is figure out whether the atmospheric components are or are not in chemical disequilibrium. And this is a Lovelock test. There's also a guy named Letterberg who wrote about this in Science in 1965. But there are different kinds of chemical disequilibrium, some of which are produced by life on Earth and others not. Now, so you can ask yourself the question, what would the Earth be like today if life were not here? If life had never evolved and done its thing? Well, we know that the oxygen that's 20% now would be very, very low. How low? I'm not sure. 10 to the minus 4, 10 to the minus 5 bars. Anyway, very low. Would we have an atmosphere like Mars, like mostly CO2? Maybe, because we think the process, well, this is another controversial thing. We have CO2 in the atmosphere, it's wet, it rains down, we have something called the carbonate silicate cycle. That is, when you get CO2 in the atmosphere, it gets taken out. When you have CO2 in the atmosphere, it gets hotter. This process has it's like a negative feedback. Some Earth scientists think the carbonate silicate cycle is a abiotic negative feedback that can regulate the temperature. Other people say, no, this is something that life on Earth has learned how to regulate and is in control of this carbonate silicate cycle. Also an important detail, in the early Earth, we don't think we had as many continents. We didn't have as much surface weathering, and the carbonate silicate cycle depends on subaerial weathering. So that's the kind of debate we're getting into, trying to figure out what does life do. And if we can't figure it out on Earth, we're trying to figure it out on Earth. Hopefully we'll discover some weird stuff, and then we'll say, oh, well, is that life? And then we'll argue about it for a long time, and then we'll learn a little bit more. But it's not easy to deal with the counterfactual of what would Earth be like if life did not exist.
Do we have any missions to monitor the Earth's atmosphere or signature that?
Do we have any Earth missions to monitor the biosignature of the Earth?
Outside?
Yes. Well, this is kind of like what Carl Sagan did before he died. I think there were 2 missions. He detected life on Earth. He detected life on Earth with the Galileo satellite that was on its way to Jupiter, and he had to turn around, look at Earth, and he detected life. One way he detected was the radio signals coming from Earth. Another way to detect life on Earth is looking at the dark side and seeing lights coming out of it. Another way to detect that is the biggest chemical disequilibrium in the Earth is the fact that we have methane and oxygen at the same time. They combine with each other. If they weren't being produced out of equilibrium, they would go on. But they're still there, and so they must be being produced by something. And so that production is an indicator of something, maybe lifelike, doing that. Another is what's called the red edge. chlorophyll has, in the infrared, an absorption. It goes from being very reflectant to not, and that's called the red edge. And if you want to detect green stuff, at least the green stuff with chlorophyll, the red edge is evidence for that. But that's kind of like, yeah, I know it's kind of like what's it called? It's after the fact that you're making that detection. But it's not easy, and so it's still a work in progress.
What about carbon dioxide? Because
Say again?
Carbon dioxide.
Yes.
Because that's what we emit, and of course plants absorb that.
Yes.
So
what about it?
That would be could that be a signature for life?
Well, my own feeling is that animals were invented to reduce the amount of oxygen in the atmosphere. Because what are we doing? We're turning, you and I are breathing, we've been breathing for an hour here. What are we doing? Turning oxygen into carbon dioxide, right? Well, animals are about, maybe a billion and a half years old, but plants, they're a little bit older, and they produce, I take back plants. Cyanobacteria was responsible for most of the oxygen in the atmosphere. And so you get oxygen, if it gets too high, then things just spontaneously combust. If you get above, now right now it's 20%, if you get to about 30% oxygen, then things just start burning. And you don't want that, so you got to lower it down. So what do? You invent animals to lower it down, to breathe it. So animals can take out the oxygen in the atmosphere and produce CO2, and then you have a cycle that is regulated at a certain level of oxygen that you're happy with, and you don't burn anything. As to CO2, carbon dioxide is the main gas of Venus and of Mars, and so far we haven't found any life there, and so we think that's a product of non-life. So it gets complicated. Arbitrarily complicated, I think, and we don't know what life is. Yeah?
Also, whatever the definition of life, so when you are...
Loudly.
Whatever the definition of life you are using...
I would say you don't need a definition, but go ahead.
So, when you're looking for life right outside, are you assuming that, those life forms will be like what you have here, like DNA-based, RNA-based, or it can be completely different?
Well, the reality is that most people are looking for humans elsewhere. They're looking for intelligent life. Remember I told you, if we find microbes on Mars, the biologists will think we're not alone, but everybody else will still think we're alone because we don't care about microbes. But because life, I have a couple more slides where I show how ambiguous this idea about life is. For example, we had an argument here about whether viruses are alive. I think there's very good evidence to suggest that the first type of life is viral life.
But that's only in art, on art. Right?
Well, this is the only thing we know about. Yes. But the whole point, we're trying to make some general feeling of what life is. Everybody thinks, oh, there's life and there's non-life, but I would argue very strongly that that's a crazy overestimation of how much we know. For example, viruses or viroids, for example, or you have in other examples, you have plasmids inside every cell in your body. Are they alive or not? Well, they think they're alive because they're reproducing by themselves inside this lovely cell that you made for them. So, I think, what was the question?
No, when you look for life elsewhere,
yes.
Are you just looking for life which is similar to what you found in art, or it can be completely different?
Well, what we're doing, as I just said, is we're looking for chemical disequilibrium that is similar to the chemical disequilibrium that life does on this planet, and is not the same as the chemical disequilibrium due to abiotic processes like photolysis from UV radiation in the upper atmosphere, or volcanoes, or plate tectonics. These are things that we think are not necessarily, or probably not related with life. So we have to say, it's got to be chemical disequilibrium, but it's got to be this type of chemical disequilibrium, not this type. And that's as far as we've taken this, and we've got a lot of work to do.
And what is the closest habitable planet?
The closest habitable planet is probably Proxima b. This is, the closest star is Proxima Centauri. So we have it's a triple star system, A and B. They go around each other in 80 years. Proxima is like an orbital period of like 10,000 years around those two. And we have found a planet around there that it might be considered habitable. But we have the problem of this very long, very bright pre-main sequence pathway for Proxima Centauri because it's an M star. I think its mass is about 0.4 solar masses. Does anybody know the mass of Proxima? Anyway, it's about 4. It's an M star, and it has a very long pre-main sequence lifetime, and maybe it's devolatilized. All the stuff, all the volatiles that you and I are made of. You and I are like 60–70% water. That's a volatile. And if there's no water on a planet, then it's hard to think of life, at least as the kind of life that we were familiar with.
So it takes some few million years.
Oh, that's a few light years away. Sure. We'll get there in about 50 years.
Yeah, one last question. Yeah.
So most of these experiments,
Say it loudly, please.
there are hundreds of planets now.
There are not hundreds, there are billions of planets.
No, what we observe. So
Oh, there are thousands of planets, about 4,000, maybe almost close to 10,000. No, they're not all being, the question is, are the planets that we've seen, about these 4,000 that I showed you, are they routinely being monitored? The answer to that is no, why bother? Except for the ones where we think we can get a signal using this new transit spectroscopy technique, because already we have done this technique with large planets that are close to their host star because their atmospheres are big. Lots of light is coming through the atmospheres. We do differential spectroscopy between the time the planet is in front and the time it's in back. We then see what the change is. Whatever the difference is comes through the atmosphere, and then we can detect water. Matter of fact, 2 months ago, there's big water detected on a planet, but it was a giant planet and it was water vapor, and every giant planet will have water vapor. So it's not an indication of something special, because H2O is the most common triatomic molecule in the universe. It's made out of H. Get rid of helium because it's a noble gas. What's the next element? O. Those are the two most common elements in the universe that make any molecules. And so H2O is everywhere. Whether it's water or not, that's an important thing. And they didn't detect liquid water, they detected water vapor in the atmosphere through this transit spectroscopy technique.
Yeah, I said lost with his saying no.
Sure.
I have the
So,
for example, the chemical signature of the planets, which are in habitable zone and which are not in habitable zone, is it distinctive, like, completed to different distribution, or like it gradually changes, or
well, we expect, well, there are a small minority of planets are Jupiter-like planets in the habitable zone. So there are very few, but there are some. Most of the planets in the habitable zone are rocky ones, which might have water on them, and we don't know yet. There are a couple, however, a small fraction, that are big and they're like Jupiters in the habitable zone, and we don't care about them because we say, oh, Jupiter doesn't make life on our solar system, so it's too hard to make life. There's not even a surface. How are you going to have, you don't have a surface of Jupiter, so you just have gas and then it turns into, I guess, gets denser and denser and denser, and then how are you going to make life there? We don't know, so let's forget about it. That's basically what we're doing. Oh, what was the question again?
My question was like, if there is a distinct chemical signature.
Distinct chemical signature, yeah. Well, let me, are there distinct differences between the atmospheres of Mercury, Venus, Earth, and Mars compared to Jupiter and Saturn? The answer is yes. Those guys have a lot of hydrogen and helium. Why do they have that? Because their gravitational fields are so large that they can hold on to these volatiles, while these little rocks close to the star could not hold on to those volatiles. So yes, there's a big dichotomy of what the atmospheres in an abiotic, no life at all scenario produce. And that's what we're pretty sure of. But right now, the only thing we can sample are the hot Jupiters, which are close. That's the biggest signal. And then we're detecting sodium, we're detecting water vapor, we're starting to detect many of the elements that we expect to be in the atmosphere of those other planets, because we see them in the atmospheres of Jupiter and Saturn.
Well, thank you, Toby. Thank you very much. Bit heavier.
Yes, that's
there
great.
is no life in it.
I'm sure there is. I'm sure there is. Thank you very much. I guess I'll be hanging around here if you have any further questions.
And tomorrow he's giving a special lecture on the Nobel Prize in Physics 2019, same time, same venue.
Charlie, long time.
Yeah. When have I seen you last? Really? Really? Okay. What do you do? You remember here? Oh, what are you working with? Grading. Oh, good.